In our last video, we talked about what pointers are, how we can create variables on the heap, and why that's useful to us. And today we're going to be talking about another concept that's associated with pointers, and that's deleting the memory that we create on the heap. One difference between memory on the stack and memory on the heap is that memory on the stack is managed for us by the system with something that we call garbage collection. This means that once you're done using a piece of memory on the stack, the system will automatically reclaim that memory and reuse it for other things. You've already seen this happening, for example, when you have a local variable within a function, and once that function returns, that variable goes out of scope. That's the system reclaiming that memory that's on the stack. Now, on the other hand, once you create a variable on the heap, that variable will stay alive for as long as you want it to. It's never going to go out of scope or anything like that. This can be really useful because now we can create variables within functions and use them once the function returns. However, this means that you are in charge of returning that memory back to the system once you're done using it. And we do this by calling delete. So let's take a look at how we would use delete in a piece of code. So here I have a simple piece of code. As you can see, all it's doing is creating an integer x on the heap. What this little parentheses 1 at the end here means is that we're initializing this new integer to have the value 1. So that's all this code is doing, and once we are done with x, we would type delete x, and it's that simple. That delete x statement lets the system know, hey, I'm done with this memory that I'd allocated on the heap, take it back, you can use it for whatever you want. The nice thing about delete is that it doesn't actually matter what x is as long as it points to some memory on the heap. So if x pointed to a double, or if x pointed to a struct that took up 16 bytes of memory, it doesn't matter whatever size it is, delete will take care of it. The only exception is when you're deleting arrays, which we'll go over in a later video. One problem commonly associated with pointers is something that we call a memory leak. And a memory leak is when you create a variable on the heap with new, but then you don't return it back to the system by calling delete before your program exits. So for example, if we took out this delete statement here, what would happen if we compile and ran our program? So we compile and we run .a.out, and we see we receive no errors, compiler errors or runtime errors in this case. But we know that when our program returned, there was still memory in use on the heap. There was a memory leak. Thankfully, there's a tool that we can use to help us catch memory leaks, and it's called valgrind. You run it just by typing valgrind and then running your executable. And let's see what happens. So we see you're performing a memory check, and we see here we have in use at exit 4 bytes in one block, and again later definitely lost 4 bytes in one block. This makes sense, right? Because we created one integer on the heap that we never deleted before we returned, and an integer is 4 bytes on my computer. So let's fix this error. So if we go back in and we reinsert that delete x, and now we compile our program and we run valgrind. Awesome. So now we see that all blocks were freed when we run valgrind. So this is what valgrind will look like if there are no memory leaks in your program. Now, don't worry if you have a memory leak, even a really large memory leak when your program ends, because the system will automatically return any memory that was left on the heap back to the system when your program terminates. So you're not going to use up all of the memory on your computer or anything like that. Yes, we have a question?
If the system automatically frees up the memory for us, then why do we need to worry about calling delete?
That's a great question. So where memory leaks start to be a problem is if you have a really long-running, large program. So say you had a program that ran continuously for hours at a time, and there's a function that was called that allocated hundreds of bytes on the heap every time it was called. If you never freed up that memory, you could actually run out of memory on the heap so that if you called new, you wouldn't be able to receive any more memory from the system. Just another good thing for you guys to know is if you ever hear people use the term freeing memory instead of deleting memory, for our purposes, they're basically the same thing and can be used interchangeably. So don't worry if you hear me or anybody else say free instead of delete. Now, there's one other good practice that you should follow when you're deleting pointers, and that is avoiding dangling pointers. So if we take a look at our code again, We'll see we deleted x here, but if you remember, x is just a variable that contains an address inside of it. So even though we deleted the memory that x pointed to, x still has that same memory address stored inside of it. This is what we call a dangling pointer. So how we would fix this is after you delete a pointer, you should always set your pointers equal to null, something like this. Now, if you want to actually use null, note that you have to include this standard def library. Otherwise, if you'd rather just put 0, setting a pointer equal to 0 or a pointer equal to null is the same thing. By setting a pointer equal to null, we help avoid a lot of errors that can be caused by dangling pointers, which we'll talk about more in future videos. For now, just know that every time you delete a pointer, it's good practice to set that pointer equal to null, or else it's considered a dangling pointer. Let's take a look at another slightly more difficult example. So if I show you the following code, we can see here that I create an integer pointer x and I create a new integer on the heap with the value 0. Then I create another integer pointer y and I set it equal to x. So what this is doing is it's taking the memory address that's stored in x and it's copying it into y. So now both pointers contain the same memory address. Now here I delete x. So clearly we're freeing up the memory that x points to. But my question for you is, are we going to have a memory leak? Should we be deleting y as well? So let's take a look at what happens when we run this code. So if we compile and then we run our code with valgrind, we see that we got no memory leaks. So clearly when we deleted x, we also deleted y. And this makes sense, right? Because if x and y pointed to the same piece of memory on the heap and we free it by deleting x, then we're also deleting the memory that y is pointing to. So in this case, if we wanted to make our code a little bit cleaner, we would set x equal to null or equal to 0, and we would set y equal to null or equal to 0, because both x and y point to a piece of memory that we no longer have control of on the heap. Now before I let you go, I want you to try one quick exercise. So if I give you the following example, what code would you put on lines 7 and 8 so that when this program exits, there are no memory leaks and no dangling pointers? That's right. First, we would delete x, so that cleans up the memory leak for us, and then we would set x equal to null to avoid having a dangling pointer. Alright, so that should be enough to get you started with freeing up memory associated with pointers. Please feel free to ask the course staff or look online if you have any questions whatsoever. Thanks.